Welcome, everyone. Today, we will embark on an intriguing journey through the world of queuing models, unraveling the principles and complexities that define the behavior of queues, a significant aspect of our everyday life. In today's discussion on queuing models, we will explore several critical components. The arrival process denotes the pattern of incoming entities or requests in the system. The queue discipline refers to how these entities are managed. This could be first come, first served, FCFS, priority based, or even random. The waiting room limit specifies the total capacity of our system, indicating the maximum number of entities it can accommodate. This limit encompasses both the entities being serviced and those waiting. The service mechanism outlines how the entities are processed, for instance, by a single server or multiple servers. The service times distribution represents the variability in service times, which can fluctuate significantly based on various factors. Lastly, the number of servers, K, refers to the count of service channels or servers present in the system. As we continue exploring the nuances of queuing models, let's focus on the core concepts of arrival and service rate and times. The arrival rate, lambda, is the average number of customers arriving per unit of time, often measured in customers per hour. From this, we can compute the inter-arrival time, which is the average time interval between the arrivals of consecutive customers. It is given by A equals 1 divided by lambda. Moving to the service end, we have the service rate, mu. This rate represents the average number of customers that can be serviced per unit time, effectively indicating the capacity of the service system. From this, we derive the service time, which is the average time taken to serve a single customer. It is computed as P equals 1 divided by mu. By understanding this rate and times, we can gain deeper insights into the functioning of the queuing model, which can guide our decisions about how to manage and optimize the queuing process. Further enriching our understanding of queuing models, we now focus on critical measures of performance. The average wait in queue, WQ, refers to the expected time an entity spent waiting in line before being serviced. Next, the average time spent in the system, W, encompasses the total time an entity spends in the system, including both waiting and service times. The length of the queue, LQ, denotes the average number of entities in the queue waiting for service. And the length of the system, L, represents the total average number of entities in the system, whether waiting or being serviced. This matrix leads us to Little's law, a fundamental principle in queuing theory, which states that the length of the system, L, is equal to the arrival rate, lambda, times the average time spent in the system, W, and the length of the queue, LQ, is equal to the arrival rate, lambda, times the arrival weight in queue, WQ. Simply put, inventory equals flow rate times flow time. To calculate W, we add the average weight in queue, WQ, and the inverse of the service rate, 1 over mu. By understanding these metrics and equations, we can gauge the performance of our queuing system and make data-driven improvement. In further analyzing queuing models, let's establish some basic relationships that apply universally across all queue systems. System utilization, ρ, is defined as the ratio of the arrival rate, lambda, to the product of the number of servers, k, and the service rate, mu. It is a key indicator of how efficiently our service capacity is being utilized. This leads to the concept of percentage of idle time, or the proportion of time when the system is not busy, calculated as 1 minus ρ. We can then extend these concepts to understand the average number of customers in the system, which is the sum of the average number of customers in the queue, LQ, and the ratio of the arrival rate to the service rate, lambda over mu. Next, we look at the average time customers spend when they are waiting in line. It is denoted as WQ and calculated as LQ divided by lambda. For the total time spent in the system, it is the sum of WQ and the inverse of the service rate, 1 over mu, which simplifies to L divided by lambda. These relationships between L, LQ, W, and WQ offer crucial insights into the overall performance and efficiency of our queuing system. Continuing our exploration of queuing models, let's delve into a common yet powerful construct, the single server or single channel model. An ideal example of this model is the MM1 queue, characterized by Markovian or memoryless arrivals and servers. In this model, several technical assumptions are made for analytical simplicity. First, there's only a single server in the system. The time between consecutive arrivals and service times are both exponentially distributed, implying a Poisson arrival process and memoryless service times. It assumes an infinite waiting room, meaning there's no cap on the numbers of customers that can wait in line. All customers are served in the order of arrival, following a first in, first out FIFO discipline. Importantly, all customers are eventually served, signifying no customers' losses. Lastly, both arrival and service rate are considered constant over time, characterizing a stationary system. The MM1 model, despite its simplicity, provides profound insights and serves as a fundamental building block in the fields of queuing theory. Moving away from single server queues, let's focus on the more complex scenario of a multiple server queue. We are examining the GGK models, specifically where both the inter-arrival and service times follow general, meaning arbitrary distributions. In this context, we made several assumptions. All K servers are considered equally skilled, implying that, on average, each one takes P time to process each customer. Each customer is served by only one server at a time, and they wait until their service is completed. The system has enough capacity to serve all demand. Using the same notation defined previously, the total capacity of the system is K times mu, or K divided by P. Lastly, the utilization of the system, a measure of how effectively the capacity is being used, is calculated as the flow rate divided by the capacity. Simplified, it is P divided by K times A, or lambda divided by K times mu. Understanding these metrics and assumptions helps us better comprehend and model multi-server queue systems, leading to improved management and optimization of these systems. Let's consider a practical example of a multi-server queue to elucidate the concepts we have learned. Suppose the average inter-arrival time, A, is 35 seconds per customer, giving us a flow rate of 1 divided by 35 customers per second. The average activity time, P, is 120 seconds per customer, which results in the capacity of each server being 1 divided by 120 customers per second. Let's say we have K, which is the number of servers, as 4. With these parameters, we can compute the total system capacity, which is K divided by P, or 4 divided by 120, equal to 1/30 customers per second. To gauge the efficiency of our system, we calculate the utilization as the flow rate divided by the capacity. In other words, it is P divided by the product of K and A, or 120 divided by the product of 4 and 35. This gives us an overall utilization of 85.7%. In essence, this means that our system is being utilized effectively, with a substantial proportion of this capacity being used to serve customers. Delving deeper into the implication of an 85.7 utilization rate, it is clear that at any given moment, there is an 85.7% chance a server is busy and a 14.3% chance it is idle. In a broader sense, this translates to an average of 85.7 of the server being occupied with customers and 14.3% being idle. When the utilization is less than 100%, that is, the arrival rate is less than the service rate, we have a stable system where the size of the queue doesn't increase indefinitely as capacity matches or surpasses demand. However, we still have to account for variability in arrival and service patterns, which can lead to waiting lines. When the utilization equals or exceeds 100%, we find ourselves with an unstable system. In this scenario, the queue size grows continuously and indefinitely as the arrival rate surpasses the service rate, and the system can never catch up with demand. This highlights the importance of managing capacity and demand to maintain an efficient and stable queue system. As the system's utilization nears 100%, several key metrics begin to rise dramatically. First, the average time in the system, also known as flow time, which is the total time a customer spends in the queue and being served, begins to increase significantly. Second, the average wait in queue, representing the length of time a customer waits before being served, also escalates. Third, the average number in the system, or work in process, which encapsulates the total number of customers either waiting in the queue or being served, escalates as well. Lastly, the average number in queue, signifying the number of customers waiting for service, grows substantially. This saturation effect underlines the dramatic consequences of high utilization on customer experience and operational efficiency. As we approach full capacity, service times and queues grow substantially, stressing the importance of managing demand and capacity to avoid system saturation.